Hello and welcome. In this video session, we will discuss on the wait and exit. So, wait is a system call used to synchronize the parent and child process. Also, there will be some use case where the parent process which has created the child process needs to wait until the child process has terminated and collect the exit information. And the exit is a system call which is used to terminate the process. So let's see how we use the wait and exit together. Okay, so when a process is running, the process has an entry in the process table. We will discuss on the process table down the line, but let's consider a data structure in which there is an entry for every process. So when the process exits or terminates, each process will have its exit status. So the process table will hold all the information, but when the process exits, it deallocates all the memory and it releases all the resources held by the process. The parent can wait for the child to terminate, and by doing so the parent can know in which state the child had exited. When parent waits for the child to exit, a signal called as child is delivered to the parent process. The wait is a system call which is used to get the information of how the child process is exited. So let's see the syntax of the wait system call. So we need to include the sys/wait.h, and wait is a system call and it returns the child process ID and it takes a pointer to an integer. We will discuss on the pointer in the example. So we have similar system call called as wait PID, which is similar to wait, but in this case we can specify the process ID of the child in which we are about to wait, and it also gives the status in which the child process has exited, and there are few options also available. So the major difference between wait and wait PID is the wait system call waits for any child, whereas a wait PID waits for a specific child from the parent. Let's see the example to understand it better. Okay, so here we have a sample program which can demonstrate the wait and the exit. So here we are creating a parent and a child process, and in this case we fork, and then based on the return value of the fork, if the fork returns a -1, we terminate it. If CPID is equal to 0, that means this is the child process. We have created a child process, and in the child process CPID will be 0. Else, in case of else, that means we are entering the parent process code. So this is the part of the code which is executed by the parent process, and this is the part of the code which is executed by the child process. Now let's say that in this example we are using a wait status here. Wait system call, and we have to pass the address of status. Status here is an integer, and let's see how this program works. The main intention of this program is whenever we have a child process executing, and in the parent process when a wait system call is there, this parent process wait in this line until the child exits from the process. Let's see the output of this by compiling the code. Wait1.c is the name of the file. So gcc wait _1.c minus object file wait_1. We have compiled the program. Let's execute the program. So here, when we execute, we get two processes in memory. One will be the parent and the other will be the child process. And the child process prints its PID and let's see the output. Okay, so we have got parent executing before wait. So based on the scheduling, in this case, the parent was executing before wait. So we got this. This is the parent process executing. Since we have a wait, these lines are not executed because this wait is like a hanging system call, which it is waiting until it gets a signal from the child process. So now after this, we got child executing first. Its PID is 3662. So the child had executed and we got the PID as 3662. Then the child was sleeping for 20 seconds and then later it exited with exit code 3. So exit is the system call used to terminate the process, and we can have the values passed to the exit to inform the parent process on what condition the child had exited. So let's see this here. So after exiting the child process, then the parent will start executing. So after the child has exited, this line starts executing in the parent. So wait in parent is done. Wait in parent is done and parent ID is 3661. So parent process ID is 3661 and child process ID was 3662 and CPID returned is 3662. So when we wait, it returns the child process ID for which the wait system call was waiting, and here we get the process ID of the child. Now if we look into the status is 768. We pass the status here and it returns the wait will fill this status by the value in which this child had exited. Let's analyze what is this value here, 768. So before having a word on the status, let's see what a status is and how to analyze the status variable. So here consider status as a 16-bit integer. So it has a bit 0 to 7 and 8 through 15. So it has 0 to 15 bits, and let's represent the bit here. Now when the child process exits in a normal or it is terminated normally, then the first 8 bits are 0 and the upper byte will hold the exit status. So in this example, the child process had exited normally without any issues and the upper byte holds the exit status. So now the value collected in status is 768. So let's analyze this here. So let's open the calculator to see this one. 768 . 768. The 768 in binary mode, if you see here, we got the lower 8 bits as 0. This is the one. The lower 8 bits are 0, and the upper 8 bits hold the exit status. So here we get 0011. So 11 is nothing but 3 here. So the child exited with the exit status 3, and the same thing is collected here. Let's change the value and run the program once again. Let's give a new value here. Let's give 1 here. So if you give a 1 here, it should hopefully change the exit status here. Let's compile this code and see. Okay, we have compiled the code, and now we are running the code. So when we run the code, so first parent process had got the scheduling, then the child got its, because of wait, parent was waiting on here, and child process got its scheduling, and it was scheduled, and it had a sleep of 20 seconds. So it is sleeping for 20 seconds. Once the child is exited, it returned the exit value of 1 in this case, and since it returned the exit, then this call, this wait, it came out of this wait system call, and now it has printed this. The wait in parent is done. So parent PID equal to wait in parent is done. So this line comes only after the child process has exited, and we collect the status. We print the CPID. CPID is nothing but the child process ID through which because of which the wait system call has returned, and then we have the exit status, in this case 256. So let's analyze the value here. 256 in decimal. Let's see the binary value. So we got this one here. So if you see this value, the lower 8 bits are 0 and the upper bit is 1. That is nothing but the exit status. So this exit status holds the, if it is a normal termination, then this is the case which we have to refer. So now let's say that the child process was killed by a signal. We will discuss about the signals later, but let's say that there is a other method of terminating the process by killing the process. So in this case, if it is a killed by signal, then let's analyze how this works here. So we have the same 16-bit here, and in the 16-bit, the upper 8 bits are unused, and the lower 8 bits are with what it matters for us in case it is killed by signal. So let's try to execute the same program again and kill the child process, and then let's analyze the status. So let's run this. So kill -9, the process ID will kill the process. So here let's execute it once again, and we get the child process ID that we need to pass it here to kill the process, child process. Let's run this once again. So this is the child process. Let's kill the process. So as soon as we killed the process, it did not sleep for 20 seconds. The child process did not sleep for 20 seconds because while this child process was executing, external trigger killed the child process, and hence the child process exited. Now, when the child process exited, the parent process was waiting for the child process to exit, and now let's see the status here. So status is 9. So let's analyze what is this 9 here. So in this case, 9, let's go back to our calculator. So 9, if you see in the binary format, it is 1001. So in this case, this is the one we need to see now. So in this case, the lower byte is not equal to 0. So this is not a normal exit. So it is an exit which is abnormal. So in this case, it is a process which is killed by some signal. So in this case, we have to analyze only the 0 to 6 bits. The 7 bit gives the core dump flag. So in this case, this is the 0th bit, first bit, second bit, third bit. So now here, if you see, the value is 8421. This is the value 9. So here we killed the process using the signal 9. So it says that this process, the child process, exited because of the kill signal 9 had sent a termination. That means the child process was killed by a signal whose number is 9. So now let's kill the child process by some other signal to analyze the output. So let's say we have some set of kill signals through which we can kill the process. So let's say we kill it using kill 8 and we run this. So 3856 is the child process. Now we have killed the child process using the signal -8. So now the status is 136. So let's analyze the output here. So decimal 136, 136. So 136 in binary form. Let's see this. Sorry, this is not the correct one. Let's go back to the binary decimal. 136 in decimal in binary is. So if you go back to this, so in this case, if it is a normal exit, we would have got the lower 8 bits as 0, but here in this case, lower 8 bit is not equal to 0. So let's go to this second use case. So it should have been killed by a signal. So we have the lower 8 bits, some value is there. So let's analyze this lower 8 bits. So we have got, this is the core dump flag. So if it is enabled, that means the core dump flag is enabled. Let's see this value. This is 1000. This is nothing but 8. So we can conclude that the child process was killed by a signal number 8. So this is the signal number 8 which killed the child process. Okay, now let's see one more example here. Now let's say that we don't want to have the status. We can also use without the status. We can just pass null in case we are not interested in knowing the status in which the child process is killed. So we can pass a null to this. Now let's compile the program once again. Okay, we have compiled the program and let's run it. Okay, so we are rerunning the program. So now the parent process is waiting here until the child process terminates. The child is executing a sleep of 20 seconds. As soon as the sleep of 20 seconds is done, the child has exited and now we can see that status is 0. So here we can see two types of usage of wait. So one is we can pass null. In this case, we are not interested to know the exit status. And if we need the exit status, then we need to pass the pointer, integer pointer basically, and the value of the integer pointer gives us idea how the child process was terminated. Now let's see the next set of examples. Okay, in this example, we are again using the wait system call. So here we created the parent process created a child process, and similar to the previous example, now this is the child process and this will be the parent process. So here inside the parent we have created one more process. So by forking we have created one more process. So we had one parent and then this first parent spawned the child process, and this is the first parent. It spawned a new process, that is a second child process. So we have this part of the code which is first child process and this part of the code which is second child process. So in this case, when we fork, so what we had discussed earlier is when the fork returns 0, it will be the child process. When fork returns an value, it will be the parent process. So here when this program runs, we have one process which is the parent process and two child process of the parent. Now in this case, at this point, or in this point, let's put the line number. So in this point, when the parent executes and waits using the wait system call, so here this parent has two child running. So specifying the wait will wait for any child process to exit. So it does not have the control, the parent process does not have the control to specify which process, which child process it is waiting on. So any of the child process which exited will cause this wait system call to return to this, and it returns the child process ID through which the wait system call was exited. So now we are calling wait system call here and again a wait system call here. Let's run this program and see the output of this. Let's compile the code. Wait 2. We have compiled the code. Now let's run it. Wait underscore 2. So if you see here, so we have the parent process 4027 is the ID, and first child is 4028 and second child is 4029. Now child 1 exited, the child 1 exited and 4028 is the process ID. So as soon as the child exited, in the parent we had a blocking system call using the wait, and once the first child exited here, we got the status of the exit of the child, and the wait returned the child process ID, and so we have printed this CPID return this. So this CPID gives the child process ID through which the wait system call has returned, and the status will tell in which status the child process has exited. So in this case, we can see that the first child exited and it has an exit status of 0, and then the second process exited and the exit status is 256. So if you see here, we have exit 0. So this is the first child status, and this is the second child status as exit 1. So which corresponds to to this value shown here. So CPID return, first one was due to the first child, and then second the weight returned was due to the second child. Now let's say here we try to change the sleep set here. Now let's say that first child slept for 10 seconds, but the second child slept for 5 seconds. Now in this case, what we can expect the output is the main process, which is the parent process, has created two child process, and the second child sleeps for 5 seconds and comes and exits. So this wait, which is waiting for its child process, returns the process ID of the second child. So let's compile this and check the output. So now we have got first child as 4087, the second child is 4086. So now if you see here, the CPID first it returned the second child process ID, which is the second child process ID is 4087. So it returns second child's process ID first, then it returned the first child's process ID, which is 4086. So what we can conclude by this is the wait system call does not have any control to wait for a specific child process, but it waits for any child process. So in this case, we had one main parent process which has two child process, and when it waits here, it can wait for any of the child process to exit. So whichever child process exit first, it returns the process ID. Then if we call the second wait, then the next process returns here. So now let's see how to use the wait PID to wait for a specific child process. Let's go to the next example, next set of example, wait 3 dot c. Sorry. Okay, so now let's demonstrate how to use the wait PID system call. So this program is similar to the previous program. Now we had the first child and the second child, which has been forked by the parent process. So the parent process forked the first child, and then the parent process forked the second child. So then here the parent process is waiting for a specific PID, that is using the wait PID, it has passed the PID to which it is waiting. So if you see the syntax of wait PID, the first parameter will be to specify on which child process the parent process is waiting. So CPID2 is the CPID consists this is the second child to which it wants to wait first and collect the status, and then the parent process wants to wait on CPID. CPID is nothing but the process ID of the first child. So the CPID holds the process ID of the first child, and CPID2 holds the process ID of the second child. So here we are waiting for the second child first, then we are waiting for the first child. Let's compile this program and see the output. We have compile the program. Let's execute this. Wait PID score 3. So now we have a main process, parent process, and it has two child process, 4173 and 4174. Now if you see here, the first wait PID returned due to second child only. Then wait PID returned due to the first child. So here we are able to wait for a specific child process ID. By this, the parent process has a control on which child process it can wait. So this wait and wait PID or wait and wait PID gives a process synchronization between the parent and the child process. So process synchronization is a method in which we can control the process so that they don't give the result which is not acceptable. For example, let's say two processes are sharing a common resource, and if there is a process synchronization, then it gives an output which is more acceptable, or the result of the synchronized process is more accurate. The unsynchronized process leads to an output which is not, the output may be a corrupted output. So in this case, we are showing the demo of using the wait PID. So now let's see the next set of example. Now let's see the example in which we are going to use wait PID, but before running through this program, let's have a small word on blocking system calls and non-blocking system calls. So a blocking call is a one in which the execution will not go to the next instruction until the blocking call function returns. Or in other way, in the previous example, we have seen that when we use a wait or wait PID, the parent process was blocking until the child process exited. So now let's now we can have a non-blocking system call as well. So when we say the function or system call is non-blocking, that means the function returns immediately, even though it does not wait for any external IO. It returns immediately without making the system to stop for the desired output. So here let's discuss about W no hang, where we can use wait PID in a non-blocking way. So here this program is similar to the previous program, but only thing is the parent process had created a child process here, and then the parent process again created the parent process is waiting for using a wait PID, and here we are specifying no hang here. So let's see this here. Let's compile this code here. So here wait PID is waiting for the child process with a no hang. So when we use no hang, even though the child process has not exited, it will not wait here, or it will not get blocked here until the child process has exited. It will carry on with the next set of instructions. So let's see this program, wait PID. gcc wait pad underscore 4.c minus o wait pad underscore 4. Let's run this program. If you see here, the parent process did not wait until the child process is exited. Because of w no high, the parent process is now a non-blocking system call. So it did not wait until the child exited. So now the same thing, if we compile, if we remove this no high and pass a 0, that means now let's see what will be the output. So now in this case, it is a blocking call and the parent process is waiting for the child process to terminate. So using the without specifying this, it is a blocking call, and once the parent process receives the exit status from the child process, then only it starts to execute the next set of instructions. Now in wait PID, if we pass a value of PID which is non-existing, so here we are passing the PID of child PID of an existing child PID, so we got the desired output. So now let's say that we are passing some value and we are waiting for the child process, but here in this case, let's say that this parent process does not have a child process with ID 80. So in this case, let's see what is the result. Let's recompile this program. Now let's run it. So here what we have got is the CPID returned is -1. So if you see here, in case of the wait PID, when it is returned in -1, we have got this error is, okay, let's see the output. Okay, we have got error is no child process, wait PID returned error is 10. So in this case, what has happened is the return value is -1, and that means let's see what is the error. The error, using p error, we can tell, we can print the error here. The error is no child process. That means whatever we have specified this 80, so this parent process does not have a child process by ID 80, so it has returned a -1. So when it returns a -1, that means the wait PID is a failure basically, and we print the wait PID returned an error in this case. Hello and welcome. In this video session, we will see how a orphan process, a zombie process, and a sleeping process are created. Let's see this with the example of a program. In this program, we include the required header files, and in the main we create a process. The fork creates a process. So the main process, which is called as the parent process, has forked the child process, and if an error has occurred during the forking, we exit the code, and in this case, this part of the code is the parent process and the else is the child process. So if fork returns greater than 0, then it will be a parent process. If ID is equal to 0, it will be a child process. So in this case, what we can observe is, as soon as the parent process is scheduled, it returns, whereas the child process sleeps for 10 seconds and then it exits. So meanwhile, when let's say that the child process is doing some calculation, in this case, just to demonstrate, we are using a sleep of 10 seconds, but let's consider some use case where a child process is doing some calculation and it takes more time for the child process to exit, and before the child process process has exited, if the parent process has exited, then the child process becomes an orphan process. So in this case, the parent process exits as soon as it's scheduled, but the child process runs, and during its execution, the child process becomes an orphan process. Let's execute this and see the output of the code. Let's compile the code. Orphan.c -o orphan test. So we have compiled the program. Let's execute it. So when we execute it, what we can see is, as soon as we execute, the parent process exits, then the child process runs. During this, the child process becomes an orphan, then later it exits. So in Linux system, when a orphan process is present, then a process of reparenting occurs, and the parent of this child process is taken by the other process. And in Linux system, usually the init process, which has a PID of 0, becomes a parent of the child process, which is in an orphan state. Let's execute this. So if you see here, the parent process has exited, but the child process is still running, and now the child process becomes an orphan process, and now the child process, after sleeping for 10 seconds, it has exited. So the moment when the child process was executing and when the parent process had already exited, then the child process was in an orphan mode, and at that time the reparenting occurred, and the child process was reparented to the other process, usually the init process. Now let's see the example of a zombie process. Let's understand a zombie process. Let's open an example. This is an example of a zombie process. Let's understand what a zombie process is. So in this case, we have created a process by forking. So we have a parent process, and now the parent process has created a child process. And if you see here, the parent process is, let's say we make the parent process to run for 15 seconds here, and the child process executes for 5 seconds. So when a child process exits before the parent process, then there is an entry in the process table. As we have discussed in the previous video session, that every process has an entry in the process table. So when a process exits, it still has a entry in the process table. So this process is called as a zombie. So in action, the child process does not exist. All the virtual memory is deallocated, and all the resource corresponding to the process is removed, but still the entry of this child process is present in the process table. So this is called as a zombie. So let's see this zombie in action. Let's compile this code and let's see this. GCC, let's compile zombie1.c minus object file zombie1. So I have created a zombie1 as the object file. So now let's run this. Let's take this command. So now let's execute this. So when we execute this, what the behavior will be, after 5 seconds, when the child process schedules, the child process exits. Now this child process becomes an zombie. Let's see this in action. So now the child process is executing, and now if we check this, sorry, Let's re-execute this. If you see here, this is the child process and it has a state called as zombie. This is the state. PS AUX gives the running process and we have grep for the zombie state. And if you see here, the child process has exited before the parent process and a child process is in a zombie mode, zombie state now. So what we have observed here is when the child process exits and the entry of the process is still present in the process table, this state is called as a zombie. So now in order to remove the zombie, we need to have a wait in the parent process. So by introducing a wait in the parent process, we can remove the zombie state of the child process. Let's see how to remove the zombie state in the parent process. Let's open the next example. Okay, this example is similar to the previous example, but in this case, we have created a fork and the parent process is present and we have a child process. So here, as similar to the previous program, the child process exits after sleeping for 5 seconds. Now, as soon as it sleeps, as soon as the child process exits, the child process is in a zombie state. Now, when the parent process performs and wait on the child process, by performing this, we are going to remove the zombie state of the child process. So before performing this state, the child process is still in a zombie state, but once this is performed, once the parent collects the exit status of the child process, the zombie state is removed and now there is no more zombie of the child process. To understand this, let's execute this program. Let's compile the program. Now we have compiled the program. Let's execute this. So the behavior would be the child sleeps for 5 seconds. Then let's run this command on the prompt and see the status. So after 5 seconds, we will see a zombie. But after this print, the zombie will be removed. So let's execute this. So let's clean up before execution. So we have executed zombie 2. So we have a zombie process here, and now if we execute once again, so the zombie process has been removed. Let's rerun this once again. So we are rerunning this once again. So we have a child process which is in a zombie state. Now after some time, if we rerun this once again, now the zombie process has been removed. So if you see this, what has happened is the child process has executed and after 5 seconds it has exited. Once the child process has exited, it was in a zombie state because the parent had not yet collected the exit status of the child process. Now once the parent performs the exit status by performing wait PID, then the zombie state is being removed. That means the entry from the process table is removed and now the child process is no more in a zombie state. A process is said to be in a sleeping state when it performs a function similar to sleep. So in this case, the parameter passed here is the unit of time in seconds. When a process is performing a sleep state, it performs similar to a no operation in assembly, and in this case this process does nothing, and once the time specified in this is done, the scheduler considers this process and schedules the process accordingly.